So welcome students for tutorial 2 of digital communication. So I will go through these problems and I will also give you the solutions, but I will highly encourage you to stop the video before I go through a particular solution and then try to solve the problems yourselves first and then look into my solutions and tally with what you have got. Okay, in that way you will be able to learn more and learn better. Okay, so the first problem is that you are given two schemes, scheme 1 and scheme 2. So these are two different modulation schemes that you have. The first one is having some signals across the circumference of a circle excuse me, whose radius is a1. So basically all these signals here has an amplitude a1, okay, and an energy that is equal to a1 square. Here you have two circles and the signals are spread over two circles. The inner circle has a radius of this and the outer circle has a radius of this. Okay, so now the question is determine the symbol error probabilities for these two schemes. It is okay to use an approximation or bound if you motivate your choice. So the clue here is that you can use either the union bound or the nearest neighbor approximation that I have taught you, and you can use both of these or any one of these. Determine the relationship between A1 and A2 such that the error probabilities from A are the same. Okay, and if A1 and A2 are selected to make the average energy equal, which scheme gives the lowest error probability? So far you have learned all the tools that are required to solve this problem. So I will encourage you to solve this problem first and then I will give you the solution. Okay. So let me go through the solution. So let's say if we assume high SNR, then we can use the nearest neighbor approximation. Okay, and in the nearest neighbor approximation, first you have to calculate the d mean of these constellations. Okay, for both the schemes. So in case of the first scheme, your d mean is basically this, which is the distance between two signals, because these signals are equally spaced within the circumference of this circle. Okay, and by the geometry of this constellation you can see that this is your d mean, and there are 8 signals, so they are basically, you know, making an angle which is 2 pi by 8 between them, or pi by 4. So this angle is pi by 4. Okay, so when you try to calculate the distance between any two signals, you use this information and apply the rules of trigonometry. So you can find out that d mean is basically this. Okay, so d mean, this distance is basically given by 2 of a1 sine of pi by 8. Okay, so you can easily calculate that. You can see that this distance is a1 and this half of this is half of d mean. Okay, so let me clear this, and then let's say this is your d mean. Okay, and if you drop a So the total angle is pi by 4, and these individual bisected angles are pi by 8. Okay, and this total distance is d mean, so this part is d mean by 2. Okay, so sine of this pi by 8 is d mean by 2 divided by this length, which is a1. So basically d mean by 2 is a1 sine pi by 8, and therefore your d mean is twice of a1 times sine pi by 8. So basically this is your d mean, and once you calculate d mean, you can easily apply the nearest neighbor approximation, and you can get your probability of symbol error. So that will be given by for the first scheme 1 over 8. There are 8 symbols, so 1 over 8 I equal to 1 to 8. Okay, and then for each signal Si you have 2 nearest neighbor. Okay, so if you consider this signal, then it has this nearest neighbor and this nearest neighbor. So for each signal you have 2 nearest neighbor. So here you have 2 here, and then the Q function of d mean over square root of 2 and 0. Okay, so and this is true for all the signals. So every signal has 2 nearest neighbors, so this will give you 2q. Okay, and this I should write approximately equal to, because we are using an approximation or a bound here. So this is 2q, and your d mean is twice of a1 sine pi by 8 divided by this. Okay, so this is the formula that you get for scheme 1. For scheme 2 you can find out the d mean also. So in the scheme 2, something is very interesting to note, that if you look into the signals that are on the inner circle, okay, and calculate the distance between them, so this distance is your d mean. Okay, and this is same as this distance, and this distance. Okay, and these distances are equal to d mean, because this is the lowest distance for the entire constellation. If you calculate distance between this signal, let's say, to this is definitely greater than d mean. If you calculate the distance from this signal to any of these signal in the inner constellations, these distances are all greater than d mean. The lowest is this distance. Okay, so that is your d mean. So all you need to calculate is the d mean for the inner circle, and that d mean is basically, this is the radius of the inner circle. So basically this d mean is let me erase this part a little bit. So this if you appreciate that the d mean is only the distance between any 2 points in the inner circle, then this d mean can be easily calculated. So let's say, again from geometry, this is the radius. Okay, so this entire distance is calculated let's say this distance is A2 root 2 by 5, okay, this distance. So if I say this as x, if I say this part as x and this part also as x, okay, then this is also x and this is also x, okay. So according to the geometry here, your d mean is twice of x, okay. D mean is twice of x, and x is basically x square plus x square is the square of this quantity, okay. So that is 4a2 square divided by 25. So x is basically a root 2 by 5, okay, sorry, 2a square. So x is basically a by 5, okay, I mean a2 by 5. So then your d mean is twice of a2 by 5 for the scheme 2, okay. So now if you use the same nearest neighbor formula, then in the numerator you will have twice a2 by 5, and in the denominator you have the same noise powers. So then those will be the expressions for probability of error for part A. In part B, you are asked to find out the relationship between A1 and A2 if these two probabilities are equal. So you equate these two probabilities, and then you can calculate A2 as a function of A1, okay. If your values are given for A1 and N0, then you can easily calculate this A2 actually, but otherwise you can give this expression like this. So you take the Q inverse of this quantity, and then A2 can be written in terms of A1 like this. For the part C, it says that if the two constellations have same average energy, so for that you need to have this. So this average energy for constellation 1 is A1 square, for constellation 2 is this, okay. You can verify this, and then if you equate this, then you can write A1 in terms of A2, and then if you compare the minimum distances for both the cases, because the minimum distances are in terms of A1 and A2, okay, and to make a comparison between the probability of errors, all you need is to check how the minimum distances are compared, because that makes the probability of error large or small, okay. So you take a ratio of the minimum distances, and you know A2 and A1, the relationship between A1 and A2 to make the energies equal, and then you can work this out, and you can say that this ratio is 1.4. So this means that scheme 1 has 1.4 times larger minimum distance. So this means that scheme 1 has a factor 2 in front of the Q function, while scheme 2 has not. Okay, oh, that is also interesting. So yeah, scheme 1 has a factor of 2 in front of the Q function, and scheme 2 doesn't have that. But at high SNR, the Q function goes to 0 very quickly, much faster than linear, and thus you just ignore the factor of 2 here, okay. All you are worried is the argument of the Q function, because the Q function falls very sharply with x, and whether you have a factor of 2 here or not doesn't matter. So you are basically comparing the argument of the Q functions like this, and then you can say that your scheme 1 will provide lowest error probability when the SNR is high, because your scheme 1 has a larger d mean compared to scheme 2. Okay, so that is how you can compare. Okay, now next let's move to the next problem. So here we have four signals S0, S1, S2 and S3, which are given like this. And let's say a digital modulation system uses the four signals in the figure to communicate over an AWGN channel with power spectral density N0/2. Okay, and you are asked to find the probability of symbol error using the union bound and expressed in um, the signal to noise ratio terms. Okay, where E is the average energy of the signal constellation. Okay, so let's look into the solution. You can stop this video or pause this video here and try working this out yourself and then look into the solution. Okay, so looking at the solution, so again for applying union bound, you have to find out the pairwise distance between all the pairs of signals. So you have four signals here. Let's say they are like this: S0, S1, S2, S3. Okay, and we don't know, let's say, how they are arranged in the signal space, but still we can calculate the distance between them. Okay, by using this formula. The squared distance between two signals AT and BT can be given by the the vector, that is the difference between the two. Okay, and taking the square of that, integrating over 0 to t. So this is essentially equivalent to the distance between the two signals, which is written in the vector form as this. Okay, so the norm square of A minus B. Okay, so so if you have two vectors, okay, let's say if this is your A and let's say this is the vector C. Okay, so the sum of these two vectors will be, let's say, this vector B. Okay, so basically A plus C in vector norm, in vector notation, gives you B. Okay, so essentially this this distance between A and B, okay, is this vector C. Okay, so C is again B minus A. Okay, or if you consider a vector which is in this direction but the magnitude is same as C, and if you call this vector as D, then basically D is equal to A minus B. Okay, so essentially we are interested in this distance between the two signals A and B. So A and B can be denoted as a vector, and the tip of this vector are the two dots. Okay, that are the two signals, let's say. So both representations are true, are valid. We have discussed this before. So this distance between A and B is basically A minus B in vector form, and then if you square that, then you get the distance between the, if you take the norm of that, then you get the actual distance, the magnitude of the distance between A and B. Okay, and then this can be written in time domain integral form like this, because these two are equivalent by definition, and then you can calculate these terms. Okay, so basically any dij between a signal Si and Sj can be written in this form, and we need to calculate that for these four signals. Okay, we need to calculate D12, D13, D23, etc. So in this form. So if we go ahead and do that, then we can see that for the terms like this, SI norm square, uh, this will be actually of this form. So all the signals have same energy, therefore we also have the same, we also have this average energy that is equal to this. Okay. Now for I equal to 0, 1, 2, we have these terms. Okay, so Si plus 1 for I equal to 0, 1, 2, which are of this form. Okay, so basically this is S0, S1, the distance between S0 and S1, the distance between S1, S2, the distance between S2 and S3, all are equal to this. Okay, so that's the way of writing. For I equal to 0, 1, 2, Si and Si plus 1, the distance between them are these. Similarly, for I equal to 0, 1, the terms like this, Si and Si plus 2, so this is basically S0, S2, S1, S3. These distances are of this form. Okay, and for the sole case of S0, S3, this distance is 0. Okay, so so with all these distances calculated, you can say so you have three unique non-zero distances. Okay, and you introduce a new notation called dk, that is equal to di uh, comma di plus k. So dk is basically the distance between any signal and another signal which is at an index that is k apart. So basically d1 is basically the distance between any signal di and di plus 1. Okay, d2 is the distance between any signal and I plus 2. So in that way you calculate d1 is always this, d2 is always this, and d3 is always this. I mean, the squares of d1, d2 and d3 are always these. So this can be expressed in the average energy term as this. d1 square is 2/3 of an average energy, d2 square is 4/3 of average energy, d3 square is 2 times the average energy. So you can create a table, okay, like this. So S0, S1, S2, S3, these are your four signals, and the number of signals which are at a distance d1 from S0 is 1, at a distance d2 from S0 is 1, at a distance d3 from S0 is 1. The number of signals at a distance d1 from S1 is 2, at a distance d2 from S1 is 1, at a distance d3 from S1 is 0. In that way you can create a table, and then you can apply the union bound. So basically you had four signals. So as you know, the union bound, if you have m signals, then the union bound should consider m into m minus 1 terms, all the pairwise distances. So this is the way of doing this. You can do this problem other ways also. So so you can see there are 12 terms. So here m is 4, so you will have 4 into 3, 12 terms, and all the 12 terms are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the Q functions. Okay, yeah, and then you have the final expression for your probability of error with union bound. You can do this problem separately by calculating all these dij's, and it should give you the same result. Okay. So let's move on to the next problem. So the next problem gives you constellation like this. Okay. So so you have a set of orthonormal axes given by psi 1t and psi 2t, and you have four signals S1, S2, S3 and S4, and you are asked to compute the average energy of the signals and sketch carefully the decision regions, and then find the probability of bit error PB of this system. Okay, and it was meant to be a QPSK. Okay, it was meant to be like this. Okay, but for DC offset and phase error in the modulator, the constellation is translated and rotated as shown in the figure. So because of DC offset, the constellation has translated. So the translation has happened because of the DC offset. So it has moved slightly to the left, and then there is a phase error that has rotated also the constellation, and now it looks like this. Okay, so instead of looking like a square aligned to the axis, it's getting translated and rotated. Okay, so the notation of the orthonormal axis is different here, but that doesn't matter. Basically, you can write all the signals. So S1 can be written as S11 psi 1t, S21 psi 2t, S2 as S21 psi 1t plus S22 psi 2t. So the concept is same, the notations are different here, but so let's see. So it has asked you to compute the average energy of the signals and sketch carefully the decision regions. So for calculating the average energy, you have to know the relative positions, okay, of these signals. So let's say the geometry is given here. So this square is A, okay. So therefore S4 has a psi 1 coordinate, that is A. Okay, and S4 has a psi 2 coordinate, that is also A actually. Now this is twice of A, okay, so that means, let's see, so S1, so this is distance is A, so S1 has basically and this is twice A, so S1 has a psi 1 coordinate as twice A and a psi 2 coordinate as A. Okay, see if you agree with me. And then S2, okay, so S2, this distance is 4A, so therefore S2 has a for S1, okay, I'm wrong here, S4 has, I'm wrong here as well. Okay, so let's say S4 has a psi 1 coordinate as A, so let me write down A, and a psi 2 coordinate as minus A. S1 has a psi 1 coordinate of minus twice A and a psi 2 coordinate of A. Okay, we were on S2. So S2 has a psi 1 coordinate of minus 4a and a psi2 coordinate of minus twice a, and S3 is remaining, so S3 basically has a psi1 coordinate of minus a and a psi2 coordinate of minus 4a. Okay, so these are the coordinates of all the signals. So once we get this, we can find out their energies, right? So the energy will be like, for S1 it will be 4a square plus a square. Basically the distance square of from the origin is the energy. Okay, for S2 this is 16 a square plus 4 a square, that is 20 a square. For S3 this energy is a square plus 16 a square, so that is 17. And for S4 this energy is twice a square. Okay, so the total energy will be the sum of all these. So this will give you 5 plus 20, 25 plus 17, 42 plus 2, 44. So the total energy E, let's say, is 44 a square, and therefore the average energy is this divided by 4. So the average energy is 11 a square, because you have 4 signals. Now find the probability of a bit error PB in terms of PB of this system. Okay, so let's see. So you have the average energy 11 a square, and these are your decision regions, basically the perpendicular bisectors of the line joining the any two signals. So for QPSK also this was like, so if you had a QPSK like this, then you had this type of or rather no, sorry, this is no, for QPSK actually these were the decision regions. Okay, so anyway, the decision regions are shown here and the average energy is calculated. Now to calculate the probability of error, you can use either union bound or nearest neighbor. So you calculate all the distances between the signals, and you can see that the d mean is this. Okay, so all the distances are same, and that is your d mean. Between 1, 2, 2, 3, 3, 4 and 4, 1, and then you can apply the nearest neighbor approximation to get the symbol error probability. So this is the symbol error probability. Okay, but in the problem you are asked to find the bit error probability. Okay, so bit error probability will be given by approximately the symbol error probability divided by the number of bits. So since this is a QPSK, or we have 4 signals, so your M is 4, which is equal to 2 to the power lambda, therefore your lambda is 2. So you have 2 bits per symbol, so therefore you divide this symbol error probability by lambda, which is 2 in this case, and you get this number. And also you can replace the average symbol energy with the average bit energy EB. So instead of 13 times E, you get 26 times EB, and you can write in this form. Okay, so I will stop here for this tutorial, and then I'll see you in the next video lecture.